Okay, in this video we're going to talk about Unit 11, Objective 3, Taylor polynomials. What a Taylor polynomial is, it's a polynomial representation of any function. So we're going to be able to take weird-looking functions and write them as a normal-looking polynomial. Well, normal-ish looking polynomial. We're going to be able to, or we're going to want to do this so we can take derivatives easier, so we can estimate values easier. So what these things would look like visually would be something like this. The green line you see is going to be e to the negative x squared power, and that blue line is our Taylor polynomial. So we're going to have Taylor polynomials of different degrees and different orders, and the higher the degree and the order of the polynomial, the more like our function, our polynomial is going to look like. So right now you can see the n equals 0 as the red line. That's going to tell us the order of our Taylor polynomial. So right now we don't really have a Taylor polynomial. We just have that blue line. Now you'll also notice right in the center it says a equals 1, and you see a purple dot at the x value 1. When we make a Taylor polynomial, we are going to center it around a certain point. So we're going to make our Taylor polynomial look a lot like our original function, but only around a certain point. As we get to the extreme ends of our graph, the Taylor polynomial is going to start to differ from the actual function by quite a bit. So if we increase our degree to 1, you can now see that the blue line looks a little bit like the green line around that purple point. Everywhere else as you go farther along doesn't really match. But we can increase again, and now the blue line covers up more of the green line farther away from the point. We can keep increasing, and every time we increase, you'll notice that a little bit more of the green line is being covered by the blue line. So our approximation is getting better and better and better every time we increase the order of our Taylor polynomial. So this goes all the way up to 10, and you can see, you know, from a little bit more than, so we'll say what, negative 0.75-ish, it's not very close. The two lines, the blue line's pretty far away from the green line. But if we go to about negative 0.25 up to about 2.25, the blue line is pretty much on top of the green line. So we have a polynomial that's going to allow us to estimate e to the negative x squared. Now, you can see in the middle of your screen it says p of 10 equals, or p of 10 of x equals 0.37 minus 0.74 times x to minus 1, and so on. That's our Taylor polynomial. So it's not a very pretty polynomial, but it's something that's easier to use than just e to the negative x squared if we're trying to find, like, what's the value of e to the negative 0.75 squared. We could use our polynomial to get that value a lot easier than we could using the e if we didn't have a calculator. So how we're going to make these Taylor polynomials? We are going to say this. A Taylor polynomial is going to be the series from n equals 0 to infinity of the nth derivative of a divided by n factorial times the quantity x minus a. Now this is going to be centered around x equals a. So on that last one we just looked at, the value of a was 1. So that's where the x minus 1 came from on that equation that we looked at. Now there's a special type of series called a Maclaurin series. And that's just a Taylor polynomial centered at 0. So a Maclaurin series is just going to be our Taylor series or our Taylor polynomial centered at x equals 0. So we would have zeros where you see A's in the series representation above. So, how we do this? Let's say generate the Taylor polynomial for f of x equals x to the third minus 10x squared plus 6 centered around x equals 3. So if we think about what we just wrote down a second ago, and I just realized I left off an exponent, so we should go back, and this is x minus a to the n power. I apologize. If we think about that, we know f of x is x cubed minus 10x squared plus 6. We know a is going to be 3. So that f, it looks like to the n power, really means the nth derivative. So we want to just start taking derivatives of f of x and see what happens. So we have a polynomial to start with. So our derivatives will eventually turn into 0. So let's just see how many derivatives we need to take. So we start off with f of x is x to the third minus 10x squared plus 6. So our first derivative is 3x squared minus 20x. Our second derivative is 6x minus 20. Our third derivative is 6. Our fourth derivative is 0, and then every derivative from then on is going to be 0. So if we look at what we're supposed to be dealing with, we have the nth derivative at a. So we want to find the 0th derivative, or just our function, at 3. Our first derivative at 3. Our second derivative at 3. And our third derivative at 3. We don't need to find the fourth derivative at 3 because it's just 0. So if you plug this in, you're going to get a negative 57, a negative 33, a negative 2, and a 6. So we know the value of our first 3 derivatives. We know the value of a, so now we can just kind of plug this in and figure out what our Taylor polynomial is going to be. So remember, a sum, or a series rather, the sigma notation tells us to add up everything from when I plug 0 in to when I plug in infinity. So if I plug 0 in for n, that would be the 0th derivative of f at a, so that's just f of 3, so negative 57, over 0 factorial times x minus 3 to the 0 power. So when I plug n in to my f to the, or f, nth derivative of f at a over n factorial times x minus a to the n, that's what I get out. Then we want to, since it's a sum, add the next term. So if I were to plug 1 in for n, that's the first derivative, which we found as negative 33, over n factorial, so 1 factorial, times x minus 3 to the n power, or to the first power. Moving along, we're going to get plus, sorry about that, plus negative 2 over 2 factorial times x minus 3 squared. And we have one more term, so plus 6 over 3 factorial times x minus 3 to the third. Now, if this were a free response question, we could stop here because now it's going to be algebraically equivalent to what we would be able to look at for our answer. But let's simplify this up a little bit. Negative 57 divided by 0 factorial. 0 factorial is just 1. x minus 3 to the 0 power is 1, so we have negative 57. 1 factorial is just 1. X minus 3 to the first is just x minus 3. So we have minus 33 times x minus 3. 2 factorial is 2 times 1 is 2. Negative 2 divided by 2 is a negative 1 times x minus 3 squared. 3 factorial is 3 times 2 times 1, which is 6. 6 over 6 is 1, so we say plus x minus 3 to the third. Now our notation for this, since it's a Taylor polynomial, we're going to say p, and we're going to call this of 3 of x equals negative 57 minus 33 x minus 3 minus x minus 3 squared plus x minus 3 to the third. Now, what this 3 here means is the degree of the polynomial. So it's a third degree polynomial because we have an exponent of 3. But this would be a fourth order polynomial. And what that means is there are 4 terms in the polynomial. So it's a fourth order, third degree Taylor polynomial that is going to help us find x cubed minus 10x squared plus 6. So that'll do it in this video. We will see you in the next one.